Dear students, today we are going to study the sulfonamide and sulphones, the topic from the third year B Pharmacy Medicinal Chemistry 3 for semester 6. In this video lecture, we are going to study the different sulfonamides and sulphones, the historical development for the sulfonamide, the chemistry of sulfonamide, classification of sulfonamide, structure activity relationship of sulfonamide, and some drugs from this category. Then folate reductase inhibitors and the sulphones. So what are sulfonamides? Sulfa drugs were the first effective chemotherapeutic agent that could be used systematically for the prevention and cure of bacterial infections in humans. What is the history behind the development of sulfonamides? In 1932, Domang began to study the red dye, that is the prontocil. It was found to protect against and cure streptococcal infection in man. Prontocil was found as inactive on bacterial cultures. Then the scientist and its co-workers contributed to study prontocil, and in 1933, first of many cures of several bacterial infections in human was reported. For the same, the scientist Domang was awarded Nobel Prize in 1939. So, prontocil was inactive in vitro but possessed excellent activity in vivo. Later on, it was found that azo linkage was reductively cleaved to release the active antibacterial product, that is the sulphonamide. This study done in 1937. Now, from the structure, you can see this is the structure for the prontocil, which in vivo reaction to give sulphonamide, that is the 4-amino benzene sulfonamide. This activity of prontocil is due to its metabolite sulphonamide. It was active both in vivo and in vitro. Based on these, various analogues are prepared by viewing to improve the antibacterial spectrum therapeutic ratio, pharmacokinetics property, and delaying the emergence of residence. So, sulfonamides are generic terms that denote different kinds. Sulfonamides are basically divided into different types, like aniline substituted and non-aniline substituted sulfonamide. For example, sulfonamides are sulfonamides and analogues. Next, non-aniline sulfonamides, that is mafenide. Next, prodrug that react to generate active sulfonamides like sulfasalazine. Next, structural analog of sulfonamide not having antibacterial activity, for example tolbutamide, that is the antidiabetic, and furosemide, that is the diuretic drug. Now we are going to study the structure activity relationship of sulfonamide. Now you can see this structure, that is the sulfonamide skeleton. It is the minimum structural requirement for the antibacterial requirement of the sulfonamide. The amino group and the sulfonyl group on the benzene rings are essential, and it should be in the position 1 and 4. You can see in the structure, this is your amino group and this is your sulfonyl group. This should be present to show the activity. Replacement of benzene ring by the other ring system or the introduction of additional substituent on the benzene ring decreases the activity. So this is your benzene ring, and on the substitution, different substitution or replacement of this benzene ring by the other ring decreases the activity. Next one, exchange of this SO2NH group by the CONH group also reduces the activity. Some heterocyclic substituents lead to a highly potent derivative, while sulfonamides, which contains a single benzene ring at N1 position, are considerably more toxic than the heterocyclic ring analog. Next, the pre-aromatic amino group should reside at the para position to the sulfonamide group. Its replacement at the ortho and meta position results in a compound devoid of antibacterial activity. So, next, the active form of sulfonamide is ionized. Maximum activity that is observed between the pKa value 6.6 to 7.4. Substitution in the benzene ring of sulfonamides produces inactive compound. Substitution of free sulfonic acid group for the sulfonamide function destroys the activity, but replacement by a sulfonic acid group and the acetylation of N4 position retain back the activity. And lastly, the lipid solubility influences the pharmacokinetics and the antibacterial activity, and so increases the half-life and antibacterial activity in vitro. Next is mechanism of action of sulfonamide. Sulfonamides are usually bacteriostatics. These are not bactericidal. These are synthetic bacteriostatic antibiotics with wide range of antimicrobial activity against gram-positive as well as gram-negative bacteria. Their use have, however, been limited due to the development of resistance. Generally, these sulfonamides are used in the treatment of urinary tract infection as they concentrate in urine before being excreted. Structurally, these are related to the para-aminobenzoic acid, that is the PABA, and thus these are competitive inhibitor of PABA. The normal utilization of PABA by bacteria from synthesis of folic acid is prevented due to inhibition of dihydroterate synthase. The latter bacterial enzyme is responsible for incorporation of PABA into dihydroteroic acid, which is immediate precursor of folic acid. From this flowchart, you will get the idea that para-aminobenzoic acid, it get converted into the folate, that is the dihydrofolate, with the enzyme dihydroteroate synthesis. Next, this dihydrofolate get converted into the tetrahydrofolate with the help of enzyme dihydrofolate reductase. And finally, this tetrahydrofolate, it is requirement for the synthesis of thymidine and the DNA. So, if the conversion of PABA to the dihydrofolate or the dihydrofolate to the tetrahydrofolate, it is inhibited, then the further bacterial infection will be avoided. Now you can see, when there is the conversion of PABA to the folate, the drugs used are different sulfonamides. And second one condition where folate get converted into tetrahydrofolate. At this step, the trimethoprim is act. This mechanism does not come in way of functioning of mammalian cell. Trimethoprim also inhibits folic acid metabolism pathway as it is a dihydrofolate reductase inhibitor. You can say DHFR. It inhibits the conversion of dihydrofolic acid to the tetrahydrofolic acid, which in turn requires for biosynthesis of purines, pyrimidines and certain amino acids. Now, next point is classification of sulfonamides. On the basis of half-lives, these are classified into the short-acting, intermediate acting and long-acting and some special purpose sulfonamide. First, we will see what is the short-acting sulfonamides. These short-acting sulfonamides have the half-life in between 4 to 8 hours and the example is sulfadiazine. Second one, the intermediate acting sulfonamide, which is having the half-life 8 to 12 hours. For example, sulfamoxazole, sulfamethoxazole. Next is long-acting sulfonamide, that is having the half-life 7 days. For example, sulfadoxine, sulfamethopirazone. And lastly, special purpose sulfonamide, that is the sulfacetamide, sulfasalazine and silver sulfadiazine. Thank you, student. In the next video lecture, we are going to study the different sulfonamides.